For centuries, people looked up at the sky with a mix of awe and frustration. Gravity is the most successful law we've ever written, and yet nobody really knows what it is. We can predict orbits with absurd precision, but the thing that keeps the dance going still feels like a mystery. Engineers trust it to place satellites, and navigators trust it to steer spacecraft past planets. In classrooms, it looks almost simple. But the moment you ask what gravity actually is, the confidence collapses into a quiet shrug again. The stars seem nailed in place. The planets, by contrast, wandered. Mars would move forward, slow, and then slide backwards, as if it were doubting itself. To an ancient observer, that was almost an insult. The heavens were meant to be perfect, yet something up there refused to match intuition. There is one thought that, once it clicks, you can't unsee. The moon isn't simply up there calmly circling. The moon is falling, and if that's true, then the whole sky, from Mars to the galaxies, stops being decoration and becomes a clue. Tycho Brahe didn't try to defeat the puzzle with philosophy. He chased it with patience. Night after night for years, he logged positions, angles, dates. His obsession carried a simple wager. If the motion is real, it will leave a measurable trace. And if it's measurable, it can be understood. Feynman liked that move. Swap argument for evidence, because the universe doesn't bargain. It answers well-posed questions. When Brahe died, his tables remained like an unfinished map. Johannes Kepler took them and searched for a shape. He began with circles, the badge of perfection. They failed. He tried combinations, tweaks, geometric tricks. Then he accepted an idea that felt wrong. The orbit wasn't a circle, but an ellipse, a squashed curve, with the sun not at the center, but sitting at a focus. That was the first blow. The second was stranger. A planet doesn't keep a steady speed. It speeds up near the sun and slows down when it recedes, yet by a strict rule. In equal times, the line from planet to sun sweeps equal areas. The third rule tied every planet together. The farther it is, the longer it takes, following a reliable, almost musical pattern. Here is the tension Feynman cared about. Kepler wrote the script, not the author. The laws tell you how planets move, not what compels them. A pattern can be admired, a cause can be used. Find the cause, and you can predict, rebuild, and carry the idea into new places. So the question becomes addictive. What deep rule makes a stone fall, and makes a planet fall without ever touching the sun? Why doesn't the sky grind to a halt? What keeps the dance going when nobody is pushing? Right there, before black holes or quantum theories, modern physics begins, not with an answer, but with a solar system that behaves far too well to be coincidence. And if that order holds in the sky, Feynman would say, it must hold elsewhere too, in tides, in double stars, perhaps at the edges where our theories start to contradict one another. Feynman arrives with a delicious discomfort. Kepler found perfect rules, but a rule is not a cause. Saying the planets move like this is like saying the melody sounds like this. Something is missing. The instrument, the reason the music repeats. And then the question appears. If it hooks you, it won't let go. What makes a planet bend its path instead of flying straight into the void? Not a tale of heroes, but clues. To set the stage, Feynman brings in Galileo. Galileo insists on a cold idea. If nothing pushes an object and nothing slows it down, it keeps moving forever in a straight line at constant speed. Not because it wants to, but because that is how the world behaves. The mystery shifts. Motion needs no excuse. change does. In other words, you don't need a force to keep something going. You need a force only when the path refuses to stay straight. That single switch is what makes Kepler's neat geometry start sounding like a confession. Newton sharpens the point. Force doesn't maintain forward motion. It changes speed or direction. Feynman teases the old picture of invisible angels pushing planets from behind. If inertia already carries a planet onward, those angels wouldn't push forwards. They would push sideways towards the sun, like an invisible string pulling towards a center. With that compass, Kepler's second rule becomes evident. Equal areas in equal times gives the game away. The pull always points to the same place. It isn't a capricious shove. It is a radial deflection, moment after moment, as if the sun is signing the trajectory. Then comes Feynman's mental detonator. The moon is falling. It doesn't fall down. It falls relative to the straight line it would follow if gravity vanished. Without force, it would shoot off and never return. With force, its path bends a little each moment, and the sum of those bends is the orbit. The moon isn't floating. It is falling while the Earth curves away beneath it. Feynman adds the human detail. Newton tried to check the idea with numbers, and at first it didn't work. The mismatch was big enough that he chose silence over certainty. Years later, a better measurement of the Earth's size fixed the scale. Newton tried again, and the fit was clear. The theory wasn't saved because it was beautiful. It was saved because the world stopped contradicting it. So Feynman drags the idea back to street level. Fire a projectile horizontally and it falls, just as if you dropped it. Now fire it faster and faster. There comes a point where, while it falls, the ground falls away too, because of the Earth's curvature. The projectile keeps falling, but it never hits. That is an orbit. By the end, the promise is on the table. If a stone and the moon obey the same logic, sky and Earth are not two worlds. They are the same problem, at different scales. And Newton, Feynman would say, has opened the door to a universal law. Feynman lands here on an idea that sounds simple but flips the whole board. If the moon falls for the same reason a stone falls, then the universe cannot be running two rule books. There isn't one set of rules for the sky and another for the ground. There is one rule, and it has to work everywhere. Newton states it like a blunt punch. Anything with mass attracts anything else with mass, not because objects are alive or because they seek a center, but because nature somehow enforces that pull. And Feynman insists you can say two consequences without a single equation. First, the more massive the bodies, the stronger the tug. Second, as you separate them, the attraction weakens very quickly, as though the effect is being diluted into space. But the decisive point isn't only how hard it pulls, it's where it pulls. The attraction always points towards the other body, towards its center. It is a force that points to a center, a force that organizes curves. And suddenly, an orbit stops looking like a miracle. Inertia wants a straight line. Gravity doesn't push you forwards. It bends you towards a point. The planet doesn't need wings. It only needs that steady sideways deflection. Even so, one ingredient is missing. The law needs a fixed volume, a universal strength-setting knob. Feynman presents it as a dial the cosmos has already set, one and the same for an apple and for Jupiter. That constant isn't decoration. It turns the idea into a tool that can actually predict. And here is the obstacle that makes this interesting. If everything attracts everything, why don't we see it on a table? Why doesn't a little ball roll towards a nearby weight? Because for everyday objects, Gravity is so weak that any interference can drown it out. Air currents, vibrations, static electricity, even heat. That is why Cavendish matters. He builds a patient device, a bar suspended from a very fine wire with small masses on it, and nearby, larger masses. Gravity doesn't yank the system, it barely toasts it, producing a tiny twist in the wire. But that tiny twist is enough to measure the law's strength. The final turn, in Feynman's style, is a serious joke. With that experiment, you don't just confirm the rule. You can weigh the Earth indirectly, deducing how much mass it must have to produce the pull we feel here. And with that, the law stops being an idea. It becomes measurable. If you can measure it, you can start weighing the universe from your own room. Feynman doesn't treat gravity as a story about beautiful ideas. He treats it like a trial. A law becomes great when it can take a hit, when the world seems to contradict it, and instead of breaking, it forces you to look more carefully. From here on, gravity stops being a neat explanation and turns into something more unsettling, a machine that predicts. Before going deep into the sky, Feynman makes a local point. If everything attracts everything, matter tends to gather and round itself out. That is why the Earth, the Sun, and the Moon are nearly spherical. And yet the Earth isn't perfect. It spins, and that spin stretches it slightly at the equator. A law that sounds made for planets also explains the shape of the world under your feet. Then he revisits the most familiar scene, the Moon, but with a twist that's easy to miss. It isn't the Moon going round the Earth, as if the Earth were a fixed nail in space. The Earth moves too. The two bodies swing around a shared point. It sounds technical, but it's a narrative key. Without it, people explain tides badly, because the lazy intuition says the Moon pulls the water, that's it, so you expect one high tide. Others imagine the opposite. The Moon pulls the Earth away and leaves the water behind. Feynman cuts through both with the same idea. The Moon's pull is not the same everywhere on the planet. On the near side, the water is tugged a little more strongly. On the far side, a little less. And because the balance of this shared fall is set at the center, not at the surface, the real result is strange and beautiful. Two bulges, two high tides, as if the ocean is obeying an invisible geometry. Here begins Act 1, the anomaly that looks as though it could kill the law. Jupiter's moons seem to run early and late, slipping in their timetable. One well-placed failure can bring an entire building down. But Roma realizes gravity isn't failing, our assumption is. We assume seeing is instant. It isn't. Light takes time to travel. When Jupiter is farther away, we see the events late. When it is nearer, we see them sooner. The law survives, and a new limit appears. Even information has a speed. Act 2. The anomaly that reveals an object. Feynman sets the stage with a simple warning. If the planets attract one another, no orbit stays perfectly clean forever. There are small tugs, interference, a constant gentle wobble. In that noise sits the decisive case. Uranus didn't quite fit. Even after accounting for known influences, a persistent deviation remained. Adams and Leverrier took the most dangerous option. Nothing is wrong with physics. We're missing an actor, an unseen planet. And they didn't merely say it must exist. They said it must be there. A telescope is pointed to that region of sky, and Neptune appears. Not luck, a discovery demanded by a law. Feynman closes by widening the scale. If it works here, does it work out there? In double stars, systems like Sirius, the dance still makes sense. even when it looks as if something is off focus. That's the cost of watching a three-dimensional orbit projected onto a flat sky. Farther still, clusters of stars and galaxies show matter gathering, as if the universe had an instinct to assemble. Even the birth of stars is suspected in gas clouds that begin to collapse. Though Feynman insists on caution, maybe yes, maybe no. And that leaves a dangerous feeling. The law works in the sea, in the planets, in light that arrives late, in a planet no one could see, and in the architecture of the cosmos. And when a law predicts like that, the next chapter can't avoid the question, what are we still missing if we want to understand it, not just use it? Here, Feynman hits an awkward break. The law works, yes, but working is not the same as understanding. And he says it with almost irritating clarity. We can describe what gravity does, but we do not know what it is. For him, the difference is between calculating and explaining. Calculating means having a rule that predicts trajectories. Explaining would mean opening the box and finding the machinery inside, like visible gears. Gravity, for now, allows itself to be calculated with elegance, but it refuses to be taken apart. So Feynman mentions an idea that excites almost everyone the first time they hear it. Imagine space filled with tiny particles, moving in all directions like an invisible rain. If everything hits evenly, nothing happens. But if the sun blocks part of that rain, the Earth would receive fewer impacts from the sun's side and more from the other. Then it would look as though the Earth is being pushed towards the sun. It sounds brilliant, until you ask the right question. If the Earth travels through that rain, it ought to feel drag, like running in real rain, where it hits you harder from the front than from behind. That drag would slow the planets down and their orbits would die away. It doesn't happen, so the mechanism fails, and Feynman's point is sharper. Every simple machinery invented to explain gravity ends up predicting an effect we do not see. Then he opens another discomfort. Gravity resembles electricity in how it weakens with distance, yet electricity between particles is absurdly stronger. The gap is a monstrous number. Some people have tried to link it to the large numbers of the universe, even suggesting that gravity's strength might drift slowly with time. Feynman treats it cautiously. If that dial changed, the sun would not shine the same, and the thermal history of the Earth would be different. The world we know would be unstable. And he leaves an image that sticks. In a spacecraft like Gagarin's or Titov's, if you let go of a piece of chalk, it doesn't fall. It hangs there because the craft, the astronaut, and the chalk are all falling together. That equality is stranger still. Gravity pulls in exact proportion to inertia. Eötvös first, and later Dicker, tested it with extreme precision. It is real, and it is mysterious. The ending is unavoidable. If there is no convincing machinery, and Newton's picture suggests instant influence, something has to change. And that is where Einstein enters. Feynman reaches the point where Newtonian gravity, brilliant as it is, leaves a splinter in the mind. In Newton's picture, if a mass changes position, the gravitational effect knows at once, as if the universe could send instant messages. And that isn't a technical quibble. It is a kind of infinite communication. But the 20th century introduces a hard rule. Information cannot travel at any speed you like. If there is a limit for signals, causes, and effects, gravity cannot be the exception. That is where Einstein enters, not as a neat historical twist, but as a necessary repair. Gravity has to respect the same limit as light. Otherwise, gravity would be the only influence allowed to cheat the universe's speed limit at all. The change, Feynman insists, is not merely adjusting the law, it is changing the language. Instead of imagining an invisible force reaching across space, Einstein proposes that gravity behaves more like a structure of the world, something that reshapes the possible paths things can take. Space and time stop being a rigid stage where events happen and start behaving as part of the story. The stage responds. Feynman highlights a consequence you can grasp without formulas. In this view, it isn't only mass that matters. Energy counts too. And if energy counts, light, because it carries energy, cannot be treated as a neutral messenger. Near a large mass, its path can be deflected, not because it chooses to bend, but because the route itself is different. That sounds odd, because we like to think light always travels straight. But straight depends on the stage. If the stage changes, what counts as straight changes with it. The most famous test was to look for that deflection near the sun. During an eclipse, when the sun's glare drops enough to reveal stars near its edge, those stars should appear slightly shifted if their light is bent by the sun's gravity. And that shift was observed. Newton was a powerful approximation, but gravity, up close, no longer looks like an ordinary force. And if it isn't an ordinary force, the inevitable question remains, how do you quantize something that seems to be geometry itself? Feynman ends the journey with a paradox. Gravity is the most democratic law in the universe. Everything attracts everything. Yet it becomes the strangest once you compare it with the rest. To show that, he puts two forces side by side without decoration: gravity and electricity. Both weaken with distance in a similar way, like echoes of the same idea, a pull that fades as you step back. You'd expect that likeness to mean they belong to the same family, perhaps even the same story told twice. The resemblance feels like family, as if nature is repeating one pattern under different masks. Then comes the punch you can't ignore. Drop down to the world of particles and electricity dominates with brutal ease. Gravity, by comparison, is almost absent, not a bit weaker. So weak it looks like an error. Except the whole universe seems built around that error. Because although it is timid on small scales, on large scales, it decides fates. It organizes orbits, builds star systems, shapes galaxies, and even tilts the path of light. And here is the deeper problem Feynman leaves like a splinter. If any theory hopes to unite the forces of nature into a single coherent story, it isn't enough to write them on the same page. People tried, under the name unified field, roll gravity and electricity into one elegant structure. But elegance isn't the point. Any unification would have to explain the most uncomfortable fact of all. Why two laws that look so similar in form end up so wildly unequal in strength? Feynman also leaves one more discomfort. Quantum physics is our most precise tool, yet gravity remains the awkward guest at that table. The conflict barely shows up in daily life. It hides. It only appears when you push reality into extremes where the very large and the very small can no longer be kept cleanly apart. So the ending isn't an answer, it's a wager. The final question isn't, how does space curve? It's sharper than that. Why did nature choose a force so weak to run the entire universe? And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.